Bismillahirrahmanirrahim. Next result f t1 t2 be linear operator on a vector space v over the field f. The linear operator mean the t1 is a linear transformation from the vector space v and the same vector space v, and t2 is also a linear transformation from the vector space v and the same vector space v. Therefore t1 and t2 is called linear operator. Then both t1 and t2 are invertible if and only if t1 composition to t2 or t2 composition to t1 are invertible. Suppose t1 and t2 are invertible. To prove that the composition of t1 t2 or t2 t1 are invertible, let t1 composition to t2 x1 is equal to t1 composition to t2 x2 for x1 and x2 are the element of the vector space v over the field f, which is also equal to t1 t2 x1 is equal to t1 t2 x2, which is since t1 are invertible, therefore by definition t1 is 1 to 1 and onto. Therefore by the element t2 x1 t2 x2 also the element of the vector space v over the field f, which these two sets are the same, therefore these elements are also the element of the vector space, this vector space v over the field f, and the images of t2 x1 and t2 x2 under the linear transformation t1 are the same, implies that these elements t2 x1 and t2 x2 are the same, as t1 is 1 to 1. Also t2 is invertible, therefore t2 is both 1 to 1 and onto. Therefore by definition of the 1 to 1 linear transformation, the image is t2 x1 is equal to t2 x2 implies that the element x1 is equal to x2. Since that is the composition of t1 t2 x1 is equal to t1 t2 x2 implies that the element x1 is equal to x2. Hence the composition t1 t2 is 1 to 1. Since t1 is onto, as t1 and t2 are invertible, therefore t1 and t2 are the onto linear transformation. There, that is for each element y contained in the vector space v, there exists an element x contained in the vector space v such that the image of x under the linear transformation t1 is y. Also t2 is onto, therefore for each element x contained in the vector space v, there exists an element z contained in the vector space v such that the image of z under the linear transformation t2 is x. Apply t1 on both sides of this equality. We have t1 t2 z is equal to t1x, and which is also equal to t1 t2 z is equal to t1x. T1x is equal to y. That is, for each element y contained in the vector space v, there exists an element z in the vector space v such that the image of the z under the linear transformation t1 t2 is equal to y. That is t1 t2 composition composition to t2 is onto. Thus t1 t2 is 1 to 1 and onto, and hence is invertible. Conversely, suppose that the composition t1 t2 or t2 t1 are invertible. To prove that t1 and t2 are invertible, let t1 x1 is equal to t1 x2. For x1 and x2 are the element of the vector space v. Apply t2 on both sides. We have t2 t1 x1 is equal to t2 t1 x2, which is also equal to t2 t1 x1 is equal to t2 t1 x2. That is, since t1 t2 are invertible, therefore t1 t2 is both 1 to 1 and onto. That is, the t2 t1 gives an identity linear operator. t2 t1 is equal to identity x1, or t2 t1 is also equal to the identity linear operator on x2 by a previous theorem, or the previous result. That is, the t1 x1 is equal to t1 x2 implies that x1 is equal to x2, that is t1 is 1 to 1. To show that t1 is onto, as t1 t2 is onto by supposition, that is t1 t2 is invertible, mean t1 t2 is 1 to 1 and onto, and the product of t1 and t2, that is the composition of t1 and t2 as well as t2 and t1 gives an identity linear operator. that is the composition of T1 and T2 is equal to identity, and T2 T1 is equal to identity linear operator according to the condition of invertibility. This is a result in our previous result theorem. That is, for each element y contained in the vector space V, there exists an element x contained in the vector space V such that the image of x under the linear transformation T1 T2 is equal to y, which is this also can be written in the form of T1 T2 x is equal to y. Since T2 is an operator on V, therefore for each z contained in the vector space V such that the image of x under the linear transformation T2 is z, that is T1 T2x, that is T2x is equal to z, that is the image of z under the linear transformation T1 is y. There, that is, for each element y contained in the vector space V, there exists an element z contained in the vector space V such that the image of z under the linear transformation T1 is y, that is T1 is onto. Hence T1 is both 1 to 1 and onto is invertible. Similarly, we can show that T2 is invertible.